So let's talk about those hidden bottlenecks in the Linux kernel, the ones that are grounding your amazing high-performance WebSocket server. We're going to figure out exactly why your rocket is stuck on the launchpad. You've done everything right. You've built a total beast of a website server, a real rocket engine full of async, non-blocking code, but then you push it to production and it just hits this invisible wall. It completely fails under load. Well, today we're going to smash right through it.
For most Linux systems, right out of the box, this is the magic number. And not in a good way. It's the exact point where your mission-critical app, your chat service, your live dashboard, will just fall over, refusing every single new connection. Okay, our mission starts with this really specific wall. It's probably the most common, definitely the most frustrating, but thankfully it's also the most straightforward problem to fix. The culprit? It's something called the file descriptor limit.
You see, in the world of Linux, there's this core idea. Everything is a file. So every time a user connects to your server, the kernel hands out what's called a file descriptor. Just think of it like a boarding pass for that connection. The problem? The kernel has a surprisingly low default limit on how many of these passes it's willing to hand out.
You can actually see this for yourself. Pop open a terminal and run ulimit-n. Chances are it's going to come back with 1024. And that's your first bottleneck. As soon as you hit that 1024th user, the system literally can't open any more files, which means it just slams the door shut on anyone else trying to connect. Now, before we fix this, you got to know about two kinds of limits. There's the soft limit, which is like your daily water ration on a long space voyage. You can change it. And then there's a hard limit. That's the absolute maximum, like the total life support capacity of the ship. To really scale up, we've got to raise both of them.
So here's the plan. It's a two-step procedure. First, you go on your limits.conf file and set a much higher system-wide limit. But, and this is a huge but that gets so many people, if you're using systemd to run your app, it completely ignores that global file. You absolutely must add the limit no file setting directly into your service's unit file. Don't skip that part.
Okay, we've smashed through the 1024 barrier. The launchpad is clear. Your server is now handling thousands of connections like a champ. But then, a new, much sneakier problem pops up. Your server suddenly can't talk to its own support systems, like Redis or your database. So, let's dig into this new bottleneck.
Yeah, this one's a real head-scratcher. All your incoming connections are totally fine, but the moment your application tries to make an outgoing connection, it fails. It's like your calm system is totally jammed. And this is because file descriptors handle the incoming stuff, but there's a completely different, and often overlooked, resource for all the outgoing traffic.
And they're called ephemeral ports. See, every single time your app needs to talk to your database, the kernel gives it a temporary port from this limited pool. Now, the default is around 28,000, which sounds like a ton, right? But in a really high traffic system with connections opening and closing super fast, that bucket can run dry way faster than you think.
And when it does run dry, these are the kinds of alerts you'll see flashing on your dashboard. Your logs will just fill up with EADDRNOTAVAIL, which basically means cannot assign requested address. You might even see 502 errors from Nginx. The root cause is always the same. You've run out of ephemeral ports. The bucket is empty.
Luckily, the fix is pretty simple. It's just a single command. We're basically telling the kernel to widen that communication channel, to expand the available port range all the way to its maximum. This gives your application over 64,000 ports to use for all its outgoing traffic.
All right, so connections are flowing in, connections are flowing out. We're feeling good, but there's one last phantom menace that can still haunt your system and drag down performance. These are the sockets that have closed, but just refuse to die.
This really gets to the most mysterious and definitely most misunderstood part of tuning TCP for scale. This is the stuff where even really senior engineers can get tripped up by following some, let's call it outdated advice from old blog posts.
So here's what happens. When a TCP connection closes, it doesn't just disappear. It enters this state called time_wait for about a minute. It's kind of like a ghost, hanging around as a safety net to catch any stray data packets. But under heavy load, you can end up with this massive graveyard of tens of thousands of these zombie sockets just sitting there, locking up memory, and using up all those ephemeral ports we just worked so hard to free up.
Okay, and this is a critical mission warning. If you go searching for solutions to this, you will find old guides telling you to enable a setting called TCP/TW recycle. Do not do this. I repeat, do not do this.
It is incredibly dangerous. It was so bad it was actually removed from the Linux kernel, because it can just silently break connections for any of your users who are behind a shared network.
The safe, the modern, the correct solution is TCP/TW reuse. Now, the difference is subtle, but it is so important. Instead of just aggressively recycling everything, reuse lets the kernel safely reclaim a socket that's in that time-wait state. And here's the key, only for a new outgoing connection, like your app calling Redis again. It is safe, it's efficient, and it's what you want.
And enabling it is just as easy as our other fixes. You just set net.ipv4.tcpwt reuse to 1 in your system's network config, and boom, the kernel can now handle all that high connection churn efficiently and, most importantly, safely.
So, with our 3 main tuning knobs twisted the right way, the case is almost closed. But before we can declare this mission a success, we need to verify our work and really nail down the core lesson from this whole thing.
All right, here it is, your final pre-flight checklist. Make sure that file descriptor limit is nice and high for your service process. Check that the local port range is maxed out. Make sure TCP/TW reuse is turned on. And, just as important, that TCP/TW recycle is definitely turned off.
And this is the payoff. When you get the tuning right, your monitoring dashboard should look something like this. You'll see active connections just soaring into the tens of thousands, the open file descriptors tracking right along with it, and that time wait count staying at a nice, healthy, manageable level. That is what mission success looks like.
So, the biggest takeaway from all this is actually pretty simple. Your awesome code, that's what scales the application's logic. But all that brilliant logic is completely useless if the operating system underneath can't handle the flow. Kernel tuning, that's what scales the pipes. So the only question left is, are your pipes big enough?